Physical reality is defined by two mandatory parameters. The first is mass, the invariant quantity of material within an object. The second is volume, the specific amount of spatial occupation that matter requires. Our macroscopic observations of rigidity, fluidity, and gaseous expansion are effectively illusions. We perceive these as fixed states, but they are temporary conditions. Under specific conditions, matter bypasses the liquid phase entirely. This solid dry ice is sublimating, transitioning directly from a solid into a thick vapor. To understand the nature of matter, we have to look past these human-scale observations and strip away our daily sensory experiences. Instead, we must shift our analytical focus down to the thermodynamic behaviors of discrete microscopic particles. Examining these particles reveals an internal architecture that eventually confronts us with subatomic anomalies. The macroscopic states we interact with are emergent phenomena, the large-scale results of localized microscopic mechanics. This model represents a pure substance. It is composed of identical particles arranged in a tightly packed, rigid lattice. Even in this solid form, spaces exist between every particle. None of these particles are stationary. They exist in a state of constant vibration. Adding thermal energy accelerates this motion. As temperature rises, the frequency and intensity of the vibration increase. Melting occurs when kinetic energy overcomes intermolecular attractive forces. The rigid lattice breaks, allowing the particles to slide past one another. At extreme velocities, these physical bonds are severed completely. The particles detach and move randomly through space at high speed, the state we recognize as a gas. Phase changes are not chemical alterations. They are thermodynamic transitions governed by the balance between kinetic energy and attractive forces. While water reaches its boiling point at 100 degrees Celsius, a simple puddle on a sidewalk can vanish at just 20 degrees. This occurs because environmental temperature is a macroscopic average of a system's energy. It does not reflect the absolute kinetic energy of every individual particle. While most particles stay near the average, a small fraction occupy the extreme high-energy tail of this distribution. When these high-velocity particles reach the surface boundary, they have enough energy to break their fluid bonds and escape into the air as a gas. Macroscopic state changes can occur locally based on the statistical distribution of energy, allowing matter to bypass systemic heat thresholds. We have established how matter moves, but we must also define what it is. This requires a shift from thermodynamics to chemical identity. In 1804, John Dalton developed the first modern empirical model of chemical composition. Dalton assumed that the atom was the ultimate indivisible unit of matter, a solid, indestructible sphere. He used the law of definite proportions to support this. He observed that pure water is always composed of exactly 11.9% hydrogen and 88.81% oxygen by mass. To Dalton, these fixed ratios meant matter was composed of whole, indivisible units. This model of the atom as a singular, solid unit survived for a century until it was tested by a vacuum tube. In the late 1800s, physicists began studying electrical discharges within glass tubes that had been partially evacuated of air. J.J. Thomson focused his research on the beam of light emitted within these tubes, known as a cathode ray. When Thomson applied an electric field to the tube, the straight path of the ray bent toward the positively charged plate. Because the beam moved toward the positive charge, Thomson deduced it was composed of tiny, negatively charged subparticles. This deflection occurred regardless of which gas or metal was used in the tube, meaning these negative particles were a universal component of all matter. Robert Millikan later calculated that the mass of this particle was several thousand times smaller than a single hydrogen atom. Dalton's model of a solid, singular unit was incomplete. Matter is divisible, containing an internal structure defined by specific electrical charges. Probing this internal structure further required a high-energy tool. Physicists found this tool in the discovery of radioactivity. In 1911, Ernest Rutherford used radioactive emissions to bombard atoms and observe the results. In this experiment, a beam of heavy, positively charged alpha particles was aimed at a thin sheet of gold foil. The baseline data was unexpected. The overwhelming majority of these heavy alpha particles passed straight through the solid gold foil without any deflection. This suggested that the gold atoms, rather than being solid barriers, were composed almost entirely of empty space. But a tiny fraction behaved differently. They hit something so dense they deflected at sharp angles or bounced directly back. Rutherford deduced that the atom contained an unimaginably dense, positively charged center that repelled the alpha particles. The scale of this density is extreme. While the atom has a radius of 10 to the power of -10 meters, the nucleus at its center is 10,000 times smaller. To visualize this, if an atom were magnified to the size of a football stadium, the nucleus would be the size of a single pea at the center of the field. In 1932, James Chadwick completed our understanding of this core with the discovery of the neutron, a heavy, electrically neutral particle residing in the nucleus. The perceived density of solid matter masks a specific internal geometry. Our physical environment is composed of atoms that are 99.99% empty space, held together by a dense, positively charged nuclear core. Zooming out from the dense subatomic nucleus, we pass through the vast void occupied by the electron field. This internal vacuum is the foundational state of all matter. Expanding further, we see these hollow atoms organized into the kinetic molecular lattices that dictate whether a substance is a solid or a gas. The solid reality we experience is the exact intersection of macroscopic thermodynamic energy and precise subatomic empty space.